Hi, welcome to Concept Based. I'm John Hepworth, and today's topic is a Year 11 Extension 1 topic. We are in the binomial theorem, and we're going to look at the concept of it today. The question that I've generated here isn't in the syllabus, it's just an exploration of the idea in this first video of this topic today. So we're going to explore the expansion of x plus y to the power of n when n is different values, 0, 1, 2, and so on. Now, you may have a certain amount of value of expansion where your teacher has said to you, if there's a question with an expansion greater than whatever in it, then you shouldn't have to do the expansion. So that generally was around about n equals 3. You might have had to expand a cube before, and it's a little bit tedious, and the ability to make numerical errors are high. But today we're going to look at a process that allows you to go for n values up to anything, and see if there's some sort of pattern that forms so we can have an abbreviated form of this general expansion. So let's have a look and start with the basic value of n equals 0. So if we were to expand x plus y to the power of 0, well, there's just a straight up rule that anything to the power of 0 is 1. So now we go to the next expansion, x plus y to the power of 1. Now, if you are doing something to the power of 1, then it's just itself. So we would have this expansion just being 1x plus 1y. All right, now we get to the one that you've done a million times because this is generally the expansion you've had to do in the stage 5 path content. And you would know this one off by heart. One lot of x squared plus two lots of xy plus one lot of y squared. All right, we're going to do one more and then we're going to see if there's any patterns that are emerging. So x plus y cubed. Now, I'll do this one in 2 stages because it makes it a little bit easier for us. So let's just do the squared expansion first, which is we've got in this line above here. So x squared plus 2xy plus y squared. And then we're going to multiply that again by x plus y. So we're going to run the x through and we're going to get x cubed plus 2x squared y plus xy squared. And then we run the y through and we get x squared y plus 2xy squared plus y cubed. And you can see why you would never expand anything bigger than a cubic, because if you had to do this for 4, it would be massive. But now let's look at the terms that we end up with here. So we've got this x squared y term appearing twice. So the coefficient of those two together is 3. Same for this xy squared. This appears twice. So if we add them together, the xy squared plus 2xy squared is going to be 3. So we're going to get these coefficients. One lot of x cubed plus 3 lots of x squared y plus 3 lots of xy squared plus 1 lot of y cubed. Okay, so that's a fair amount that we've done there. And what I'm going to try and do now is have a look at the patterns. So first of all, we can see on the left-hand side here, we go from x to the power of 0 to x to the power. Why did that drop in there and change colors? Let's go back. Not sure what that mod was. X to the power of 0, x to the power of 1, x to the power of 2, x to the power of 3. You can see that the leading term is always going to be x to the power of whatever the brackets are. So our first term is going to be some x to the n term. Then when you look in the next term, you can see that it's dropped by 1 for the x. Now 0 can't drop by 1 because it already has. But here x is to the power of 1, and over here x doesn't appear, which is like x being to the power of 0, because x to the power of 0 is 1. So we have it dropping by 1. Here in this next one, we can really see it. The x goes from 2 to 1 to 0, because again, it's not over here, so it's like x to the 0. So we can always see as we go along these expansions for terms, you have x to the n, then in the next term, you have x to the n minus 1. In the next term, you have x to the n minus 2, and so on until we run out of terms. But the y is also doing something as well. The y is doing the same thing, but backwards. You can see that the y in this question could actually be written as y to the 0. And then in this one, it's y to the 1 here, but then it's y to the 0 there. And then in the next one, it's y squared, and then y to the 1, and then y to the 0. So it goes downwards, or you could say essentially that it goes upwards the other way. So it's y to the 0 plus y to the 1 plus y to the 2 until that goes. And if we were to keep on going and write some final term, it would be x to the 0, y to the n. Now I have left a little bit of a gap in front of these things here. So what I want to do is explore the amount, the value that's in front of these terms. So let's have a look at what we can see up here. Now it starts off and the value is always just 1. 1, 1, 1, 1. And here this 2 is the first one that appears that's not a 1. So we've got that in the expansion of our quadratic. But then in the cubic, we get the values 1, 3, 3, 1. So let's write these out and see if we can see a pattern here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This pattern is the beginning of Pascal's triangle. And what you need to do to get the next term is just add the two terms that are above it. So you can see that 1 plus 1 here gives us that 2 in the middle. Whereas if we have these imaginary zeros off the side here, 0 plus 1 gives us 1. But we also always saw that the first leading term there was a 1, and that the last final term there's always a 1. It's just these terms in the middle here. So we'd get 1, 4, 6, 4, 1 here if we were, to expand a quartic. So now, with this idea, you actually have the power to do a huge expansion very, very quickly in this binomial expansion. For example, this next line here, this quartic expansion, if we were to say x plus y, oh, bless me, x plus y to the power of 4. Okay, 2 sneezes, that's enough. I might edit that out. So x plus y to the power of 4 equals, we've got the one term first, and we know the first is x to the power of 4. Then we have a 4 coefficient, x to the power of 3, and now y is raising in power to 1, plus 6, x to the power of, oops, not 4, 2, y to the power of 2, plus 4, x to the power of 1, y to the power of 3, plus y to the power of 4. And look how fast that was to do an expansion of x plus y to the power of 4 straight out of this Pascal's triangle pattern that we can see here. Now we can go a little bit further here and we can look at these values of 1, 4, 6, and wonder, well, where are they coming from? And can we even generalize those numbers? Well, of course we can. We have done combinatorics before, and let's look at combinatorics. If we had a group of no people and we chose no one from them, then how many ways could we do that? Well, we could do that one way. If we had one person and we chose no people from them, we could do that one way. And if we had one person and we chose that one person, we could do that one way. If we have two people and we choose no people, we'll get 1. If we have 2 people and we choose one person, there's 2 ways of doing that. And then if we had 2 people and we chose 2 people from that group, there's only one way of doing that. And look at what we're getting. We're getting Pascal's triangle. 1, 1, 1, 1, 2, 1. So therefore, on our next line, when we were doing a cubic expansion, we would expect to see that these values are going to create the 3, 3, 1 situation. And if you do go and check these on your calculator, they do actually create the 1, 3, 3, 1 situation. So the way we can actually work out what coefficient we have in any expansion of x plus y to the n, the coefficient is going to be nc, whatever term you are at. So n being the power, and then let's say we're at term k, then the power of x, remember x started at the power of n, and it dropped down every time we went along. So if we went along to the term k, we would be at n minus k power for x. And the y value would be, it's increasing. It starts at 0 and goes up. So the kth term would be y to the k. And we can actually go straight to any term in the expansion of our binomial by putting some k value in, and we would get that expansion. Now, obviously, these expansions can change. We have to start k from 0 and go all the way up to the n value if we want all the terms, and then add them all together. And the way we add things together is we write a summation. A summation from k equals 0 of nck, x to the n minus k, y to the k. And that's how we expand any binomial.